Good morning, dear student. In last lecture, we will discuss the nucleophilic attack on the coordinated ligands such as carbonyl and polines. So, in this case, these carbonyls and these polines are electrophilic in nature. So, nucleophile can attack on this electrophilic center, and therefore we will discuss, that is, the nucleophilic attack on coordinated polyene, that is electrophilic coordinated polyenes. So in this lecture we will discuss the electrophilic attack on coordinated polyenes. Student, we already discussed the nucleophilicity order for a nucleophilic attack on coordinated ligands. So the order, that is the nucleophilic susceptibility order, is reverse in this electrophilic attack on coordinated ligands. So it is just reverse to that of nucleophilic attack on coordinated ligand. So in this case, this cyclopentadiene, which has a more tendency to attack by electrophile, because it is a least tendency for nucleophilic susceptibility or nucleophilic attack. Therefore, the cyclopentadiene has more electrophilic susceptibility as compared to other ligands which is attached to the metal atom. So in this lecture we are very much interested in the ligands or the complexes which shows electrophilic attack, that is metallocene. So what is this metallocene? So these metallocenes, so we are very much familiar with the metallocene, that is ferrocenes. So we already discussed in last year what is ferrocenes, what are the chemical properties of ferrocenes and different types of reactions of ferrocenes. So these metallocenes are nothing but in these metallocenes the metal atom is encapsulated between two cyclopentadiene rings. They are considered as a metallocenes. So in this metallocenes the metal atom is encapsulated between two CP ring. So they are considered as a metallocenes. So generally vanadium, chromium, manganese, Fe, cobalt and nickel shows vanadium, chromium, manganese, Fe, cobalt and nickel forms metallocenes. So generally these metal ion, that is vanadium to nickel of 3D series, forms metallocenes. So if you consider the metallocenes, so let us consider one example. If you consider the vanadium and this Cp2 ligands which is attached to the metal atom, then it is known as validocene. If chromium is attached, then it is chromocene. If iron is attached, then it is ferrocene. So we are very much interested in ferrocene. So ferrocene is the first metallocene compound which is derived. So ferrocene, so if you consider a structure of ferrocene in which Fe which is attached to this cyclopentadiene ligands, again the another cyclopentadiene is there, and both these cyclopentadiene has hapticity 5. So you can write eta 5 C5H5. This ligand is also hapticity 5, that is C5H5, eta 5 C5H5, means all the carbon atoms are attached to the metal atom. So if you consider this species, generally not all metallocenes follow the 18 electron. but this ferrocene it follows 18 electrons. So if you count the electron, then Fe contribute 8 electron, and this cyclopentadiene contribute 10 electrons. So total it is an 18 electron species. Other metallocenes does not obey the 18 electron rule. So less than 18 electron metallocenes are also formed. So this ferrocene is 18 electron complex. So in this, if you consider this ferrocene or this cyclopentadiene is a nucleophilic in nature, it is electron rich. So we know that after dissociation of this ferrocene, if, if you dissociate this ferrocene, then we get a cyclopentadiene, two cyclopentadiene having a negative charge. So you can write this as two cyclopentadiene having a negative charge. So it is aromatic in nature, and therefore it will shows uh, the reactions such as electrophilic substitution reaction similar to benzene. So benzene, it is also aromatic in nature, it will shows electrophilic substitution reaction. So this cyclopentadiene, it is also aromatic in nature, and it will shows electrophilic substitution reaction. If you consider this cyclopentadiene, it is a sigma donor and weak pi acceptor ligand. So it is not a strong pi acceptor ligand, it is a sigma donor, but it is a weak pi acceptor ligand. So if you consider this metal atom present in this metallocene, for example in ferrocene, so due to the negative charge on this cyclopentadiene, the ferrocene, the Fe atom which is present in this ferrocene, it have a +2 oxidation state, or it is present in +2 oxidation state. So if we count the oxidation state, that is Fe Cp twice, and then if you count the oxidation state, then it is X plus minus 2, which is equal to 0. So X is equal to +2. So the metal atom is in +2 oxidation state. All these metallocenes are low spin complexes. All these metallocenes are low spin complexes. So if we consider the d orbital splitting in this metallocene, so let us consider the d orbital splitting of these metallocenes. So we have already discussed, whenever the ligand is attached to the metal atom, then the d orbital is split into two orbital, two energy level orbital, that is lower energy T2g orbital and higher energy Eg orbital. But in this case, in case of metallocene, the d orbital is split. So it will split into two orbital. It is denoted as E2g. So it is G-red, and it is 2 orbital. So it is E2g. So it is dxy and dx square minus y square orbital. So lower energy dxy and dx square minus y square orbital. Then another is, it is A1g. It is denoted by symbol A1g. No doubt it is G-red, and it is a single orbital, therefore it is A1g. So it is your dz square orbital, and again there is a 2 orbital, that is it is E1g star. It is your antibonding orbital. So it is dyz and dzx. So you should remember this energy level diagram, or this splitting of d orbital in case of metallocene. So in this case, the lower energy dx square minus y square orbital, then dz square orbital, and then dyz dzx orbital. So this E2g orbital, it is a weak bonding orbital. This A1g is your non-bonding orbital. This A1G is non-bonding orbital, and this E1G star is your anti-bonding molecular orbital. Anti-bonding molecular orbitals. So if we consider the energy gap between this A1G, that is non-bonding and anti-bonding orbital, the energy gap is very large, and therefore this the electron is not, the extra electron not goes into this antibonding orbital. So instead of it will goes into this antibonding orbital, it will pair, and therefore all these metallocenes are a low spin complexes except the magnocenes. So manganese MnCp2. So this MnCp2, it is a high spin complexes. High spin complexes. So all other metallocenes are low spin complexes, but you should remember that MnCp2, it will shows high spin complex because the energy difference or the energy gap between this non-bonding orbital and anti-bonding orbital is very less in case of this MnCp2, and therefore it will shows high spin complex. But if you consider MnCp2 star, that is all this cyclopentadiene is substituted, then it will shows low spin complex. So there is a pairing of electron, low spin complex. It is a pairing of electron. So you should remember all metallocenes are low spin complexes, but the MnCp2 is a high spin complex, but the substituted MnCp2, it is also a low spin complex. So many times the question is asked, that is the question is asked on a metal carbon bond length. So in these metallocenes you should remember that as the number of unpaired electron is increases, the MC bond length is also increases. So you should remember this thing, that is as the number of unpaired electron in metallocene is increases, so number of unpaired electron is increases, then MC bond length, metal carbon bond length is also increases. MC bond length is also increases. So you should remember this thing. So let us discuss one by one. So if you consider first metallocene, that is VCP2, and if you find out either it is diamagnetic or paramagnetic, then we know that this cyclopentadiene has a negative charge, therefore this metal atom is in +2 oxidation state. So if you consider vanadium, it is 4s2 3d3 configuration vanadium, but it is in +2, therefore it is 4s0 3d3 configuration. And again, if you feel the electron into this energy level diagram, that is dx square minus y square, then it is dz square, and then it is dyz and dzx. Then so only 3 electron is there, so 1, 2 and 3. So it has 3 unpaired electron, and therefore it is paramagnetic in nature. It is paramagnetic in nature. Similarly, you try for other metallocenes. For example, let us consider for ferrocene, that is FeCp2. FeCp2. Again, this Fe, it is in +2 oxidation state, so its configuration is 4s0 3d6. And again, if you feel this electron into this E2G, then it is A1G, then it is E1G antibonding, then first, second, third. So next electron is not goes into this antibonding orbital because the energy difference between these two A1G and E1G star orbital is very high, and therefore there is a pairing of electron. So the next electron goes into this E2G orbital, therefore fourth, fifth and sixth. So in this ferrocene all electrons are pair, and therefore it is diamagnetic in nature. It is diamagnetic in nature. It is diamagnetic in nature. So this is regarding to the magnetism, either it is paramagnetic or diamagnetic. So it should remember this d orbital splitting, that is the d orbital is split into two orbital, that is first d E2G orbital, that is dxy and dx square minus y square, second that is dz square, and third one that is doubly degenerate, that is dyz and dzx orbital for metallocene. So many times the question is asked on MC bond length, diamagnetic nature. Okay, so if you consider this metallocene, so these metallocenes are electron rich. So if you consider this metallocene, for example, they are observed in three forms. So if you consider this metallocene Fe, it is attached to this cyclopentadiene again. Fe attached to this cyclopentadiene. So if you consider both these cyclopentadiene are superimposable on each other, and therefore if you consider it is in eclipse form, this ferrocene it is in eclipse form. So both these cyclopentadiene in same plane, therefore it is considered as a eclipse form. And if you find out the point group of this eclipse ferrocene, then it is D5H. You should remember the point group, that is D5H. So in this case the point group of this ferrocene is D5H. And if you consider another possible orientation of this ferrocene, then Fe it is attached to this cyclopentadiene, and in this case so these two cyclopentadiene which is attached to this metal atom are not in same plane, they are in different plane, and the bond angle between these two cyclopentadiene is 60 degree, and therefore it is in staggered form. So it is staggered form. This ferrocene it is in staggered form, and if you find out the point group, then it is D5D. So you should remember this point group, that is ferrocene in eclipse it will shows D5H point group, and in staggered form it will shows D5D point group. So if we consider the staggered form, it is observed in solid form. So solid ferrocene it will shows solid ferrocene it is observed in staggered form, while this eclipse ferrocene it is observed in gaseous form. Gaseous form. So you should remember this thing. And another, if you consider the Fe, it is attached to this cyclopentadiene again. So in this case, if you consider the point group of this ferrocene, then it is only D5 point group. So you should remember only these two, that is one is eclipse, another is staggered form. In eclipse it is D5H, and in stagger it is D5D point group. So if you consider the reactions of ferrocene, so the ferrocene is aromatic in nature, and it will shows electrophilic substitution reaction such as benzene. So if you consider the first reaction, that is alkylation of ferrocene. So if you consider Fe, so alkylation of ferrocene, that is RCl in presence of Lewis acid AlCl3, product of alkylation. Then in this case here what do you get? Fe. So this ferrocene is nucleophilic in nature, that is it is electron rich and it will attack the carbocation which is generated in presence of Lewis acid. So in this case we get the R group is attached one of the cyclopentadiene ligands. And if you consider further we carry out the reaction with RCl and AlCl3, then this R group which is attached, this R group which is attached to this cyclopentadiene, it is electron rich and therefore it will donate the electrons to this cyclopentadiene, and therefore it is electron rich. And another addition, that is another R group is also attached to the same ring, it is not attached to different it is not attached to other cyclopentadiene. So in alkylation the substitution is going on, the substitution, that is second substitution, is also on same ring, that is Fe. R is attached to this cyclopentadiene, another R group is there, and this cyclopentadiene. So in alkylation the R group which is attached to this cyclopentadiene, it is electron donating group, and therefore if we carry out or if we further add this methyl chloride in presence of Lewis acid, then the same ring will shows the electrophilic substitution reaction. But if you consider the second reaction, that is acylation reaction, acylation of ferrocene, that is second acylation of ferrocene. So again we consider Fe attached to this cyclopentadiene ligand, and then acylation, that is RCOCl, acyl chloride in presence of Lewis acid. Then in this case the first the carbocation which is generated, and this ferrocene is electron rich, therefore it will shows electrophilic substitution reaction, and we get Fe, C double bond O, and this is your R group. So if you carry out the same reaction with this intermediate which is obtained, then in this reaction RCOCl in presence of Lewis acid. So if you carry out the same reaction, then the electrophile does not attack on the same cyclopentadiene. So in this case if you consider this C double bond O R group is electron withdrawing group, and therefore it will decreases the electron density of this cyclopentadiene ligand, and therefore if we carry out the reaction with another molecule of acyl chloride in presence of Lewis acid, then the next molecule is attached to second cyclopentadiene ligand. So it is not attached to the same cyclopentadiene ligand. So we get here C double bond O R, here Fe, and the another cyclopentadiene undergo electrophilic substitution reaction. So you should remember, in alkylation electrophilic substitution is occur in same ring, while in acylation the electrophilic substitution is occur in two different ring. So this is regarding to the acylation and alkylation reaction. So this is all about ferrocene. In next lecture we will discuss the question which is asked in SET and CSIR NET exam regarding to this metallocenes, and further we discuss the remaining points of this chapter. Thank you.